Hey everyone, in this video we're just going to continue on with what we know about quadrilaterals, and we're going to just look more about the trapezoid and the parallelogram. So in this first exercise, it's just business as usual. So we want to take this quadrilateral, our STU, and our coordinate points are given. We want to show that it's a trapezoid but not a parallelogram. So let's take a second and plot that. -4, 4 is R, 2, 7 is S, T is 5, 2, and -7, -4 is U. Okay, so we can see our shape. We kind of feel comfortable saying that it's a trapezoid, but we want to be safe here. We want to show our work, and we also want to show why it's not a parallelogram. So the easiest formula I can do that with is slope. Slope is the only one that can tell me if there's parallel lines or not, and that's the only property of a trapezoid. So property would be that one pair of opposite sides are parallel. Let's go see what we have here. So for RS, when I look at the slope, it would simplify to up 1 over 2, right? It looks like I'd be dealing with up 3 over 6, but that simplifies to 1 over 2. Okay, for ST, looks like we're going down 5 over 3. UT is also going to be up 1 over 2. So if I'm looking at that, it looks like it would be up 6 over 12. So if it's up 6 over 12, that's going to simplify. And then finally, last side, UR. That appears to be up 8 over 3. Okay, so we got our 4 slopes. Notice I've clearly labeled which one was each side, just so we're covering all our bases there. But then the only thing left to think about is what we see here. So I see that we have at least one pair of opposite sides that are parallel. So I can say RS is parallel to UT. Okay, or I could just say one pair of opposite sides parallel. Therefore, RSTU is a trapezoid. And then I also know that both pairs of opposite sides not parallel. Therefore, RSTU is not a parallelogram. Okay, remember I could use that symbol for parallelogram if I want. Okay, so in this case, remember, this is a coordinate geometry proof. We know it right off the bat because there's coordinates involved. We can see a graph. That's when we do a proof like this. Okay, so we do the math first, whether it's slope, distance, midpoint. We explain what that math showed us and what property that we have, and we make the statement of which shape it is now. Okay. When we get to something like exercise 2, we're starting to work ourselves back into a different style proof. So here's just an explanation question. It says, in the diagram shown, we know that angle 1 is congruent to angle 2. We want to lead us to why we know that means the shape RTUS is a trapezoid. So it's been a while, but think about 1 and 2. Think about how they form that Z shape. That means I'm looking at congruent alternate interior angles. And they are formed by parallel lines. Okay, so that leads me to believe that this side RT is parallel to this whole side of RU, because those are the inside lines that I'd be thinking about. Okay, so RT is parallel to SU, and now I'm in the same place I was again. So since I was able to find that, I can say one pair of opposite sides are parallel. Therefore, RTUS is a trapezoid. Okay, so it's the same kind of concept. We're looking for what reason we have to state that this shape is a trapezoid or a parallelogram, depending on which one we're looking at. Now, 3, we start to build back to what we know and how we do the old style of proofs, right? These are your Euclidean proofs. This is the statement reason, that formal idea. But we're not going to go too crazy on our own. We have our statements already set up for us. So, as a reminder, no matter what happens when we're doing statement reason, your first reason should be the given information, right? I was told right here that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. So I need to use that. So that's my first statement, that's my given. So I'm going to go investigate that a little further. Okay, so I have angle 1 and angle 2, which are congruent. And if I look closely, that can lead me to say that AB is parallel to DC. Right, I saw that Z shape. Again, I have my alternate interior angles. So I can say congruent alternate interior angles, which are formed by parallel lines. If I look at the other part of that, like angle 3 and angle 4, now those angles are different. They're up here and here. They still use this same line, but their Z is going to be a little bit different. It's like rotated around a little bit. That's okay. It can be backwards, but that's how it leads me to AD being parallel to BC. So it does matter which one's attached to which. But either way, I've just showed that both pairs of opposite sides are parallel, which is one of our properties. We know then if both pairs of opposite sides are parallel, then it's a parallelogram, which is what I was trying to prove. And that's what I'm going to say. Both pairs of opposite sides parallel in a parallelogram. And then that was enough, right? So we show our shape is parallelogram by showing one of its properties. Okay, so we show either opposite sides are congruent, opposite sides are parallel like we just did. So opposite angles are congruent. Okay, one of those ones are probably easier to use, or even if the diagonals bisect each other, we would know it's a parallelogram, right? So we just find one of those properties to show it's true, and then we're good. Okay, on the diagram, quadrilateral RSTU is shown with vertices given. Prove that RSTU is a parallelogram using coordinate geometry. So in this one, it's already nice for us. It's already drawn in. So we're just going to take those slopes quick. So if I look at each one, RS is up 3 over 9. Simplifies to 1 over 3. ST is up 5 over 3. UT is again up 3 over 9, so up 1 over 3. And you are you, that's going to be again up 5 over 3. So we can easily say that this is a parallelogram because we have both pairs of opposite sides parallel. Therefore, RSTU is a parallelogram. Remember, there's multiple ways we could have done it. I could have drawn in the diagonals and show they bisect each other with the midpoint formula. I could do the distance formula 4 times to show opposite sides congruent. Slope's just the fastest one, in my opinion. Okay, but it does ask me to verify that RU is congruent to ST. So remember our distance formula, RU. If we plug that in, 0 subtract a negative 3 squared plus 3 subtract a negative 2 squared. 3 squared is 9, 25, and we get the square root of 34 for RU. ST, we're doing 9 subtract 6 plus 6 subtract 1. We end up with 9 plus 25, also equal to the square root of 34. So we don't have to make any statement there because we just showed the two are congruent using that distance formula. Okay, last idea for this. Now, this is different than the proof we did in exercise 3. Instead, we're given that it's parallelogram. That makes it so much nicer because now we know all the properties, right? We know all the properties are fair game in this one. So there's a bunch of different ways we can go about proving this parallelogram. So I gave us one route and we're going to stick to it. But again, just like it was when we did it the first time around, proofs are not a one answer kind of question. You can do it however makes sense to you, which is the nice thing about them. But no matter what, the one thing that should stay consistent is no matter what, our first reason should be the given, right? And then I can look and see that that given information is what I wrote down in the statement first, and our reason is just because we were told it. Okay, then the next thing we do here is we talk about how AB is parallel to DC and AD is parallel to BC. So think about the shape it is. It's a parallelogram, so in a parallelogram, opposite sides are parallel. And we've kind of been on this trend the whole time, but that means it can lead me to angles 1 and 2 that are congruent, and angle 3 and angle 4, because we have parallel lines form congruent alternate interior angles. Now here's a throwback for us. It's been a little while since we've used it, but anything that's on top of each other using both triangles like this, BD congruent to BD, anything congruent to itself, that's our reflexive property. And finally now, so if we look, we had two triangles that we're proving. Because anytime we're trying to prove a side or an angle and there's a triangle involved, I'd still try to prove the triangles first. Remember, that was always our goal. If we could prove the triangles first, that leads us to anything else we want. And we'll talk about how in a second. But if I look at these two triangles, one being here, and the other being here. That's how we knew we had that reflexive, that overlapping piece. But if I just highlight one of them for a quick moment, And I just take one of those separate. Now again, still remember, it does not have to be perfect. Your sketches are never going to be graded on you. But if I look at this, right, I have A, P, D. I had that reflexive property. I also have an angle 1 and angle 4. So this is how I kind of remind myself which method I just proved the triangles are congruent with. Remember, we needed 3 checks. So either 3 sides, 2 angles and a side, or 2 sides and an angle, depending on how we work it. Okay. But in here, notice everything falls on this line together. The side is in between the 2 angles. So my reasoning here is angle, side, angle. So I know those 2 triangles are congruent by angle, side, angle. And then any corresponding pairs of sides or corresponding angles are all going to be congruent thanks to CPCTC. Corresponding parts of congruent triangles are congruent, which should make sense anyway, because A and C are opposite angles that are congruent. A, B, and D, C are opposite sides that are congruent. So I already knew those were congruent anyway, but we're just using our properties to verify some of our parallelogram properties here. Okay, so we're going to get back into proofs a little bit here as we move forward in the next week or so, but it's all proofs that we've already done, a style we've already done before. The only thing new, only thing I'm worried about as I do it is that we now have so many more properties that we know offhand, right? We know a lot of parallelogram properties, and that's what makes this so nice. Okay, thanks for watching, guys. We'll regroup again.